operations. And first, I would like to review what we've done so far. So far, we based everything on a static lattice model. Smile. Static lattice model. That is, we worked in a limit of immobile lattices. We allowed only electrons to move, and we assumed there is no motion whatsoever of the lattices. So, and T equals 0. Actually, you mentioned the temperature only once. When? Relation to... Okay, I'm not sure what Nadia mentioned, but you covered the Fermi-Dirac distribution, which has temperature dependence inside. And then you derive specific heat also, which has some simple temperature dependence. However, this limit can describe some properties, but many things are missing. And in classical theory, this limit comes to this, temperature 0. Because in classical theory, as soon as you raise the temperature, the atoms have to move. That we'll also do in a few minutes again, but you know this from classical theory. In quantum theory, you know from the Heisenberg uncertainty principle that the more you stop them from moving, the more you localize them, the more they have to move. So you cannot have it static. And as soon you cannot have non-vanishing momentum. They have to move. So we are coming to some problems. We have to consider also the lattice of ions moving. What we've done so far actually made sense for metal systems. Why? Because most properties are determined by the electrons at the Fermi energy. So we took them into account and we managed to derive something. However, for the insulators, they don't have any degrees of freedom. And you simply don't have enough to describe their properties. So we are actually not doing it. We haven't done anything for the insulators. So the fails, this model fails. Let's see, first for the equilibrium properties. Like specific heat. If you don't take any vibrations into account, you will get a linear dependence of specific heat with temperature, which is correct up to some, I'm not sure, 10 Kelvin behavior. Then in reality it becomes much steeper, like 10 on the power of cube. And this is because of the lattice degrees of freedom. Then what else? Obviously, thermal expansion. As you heat up, the lattices are likely to become get larger lattice parameters, except graphene, which shrinks with temperature, has a negative thermal coefficient at some temperatures. There is some temperature range in which it's negative. So this is quite obvious. Also melting. You cannot explain at all in the static lattice model. And the other group of properties are transport properties. Let's mention here first the thermal conductivity of insulators. Well, this is just a selection of what you could raise yourself. I mean, there are many more detailed properties which are not mentioned. Insulators. I think in Ashcroft there is an example of a spoon of metal which heats up immediately. You take just a tip, you put in a hot tea, everything is warmed up. If you put a ceramic spoon or ceramic whatever, it won't be so fast, but eventually it will heat up. It is known that materials which are good conductors, electrical conductors, are also good thermal conductors, which is obvious. But they also can conduct heat if they are insulators. And however, we have no ways of describing it because there is no electrons and the Fermi energy. So we have to take into account the ionic degrees of freedom. Superconductivity. You know about superconductivity of the resistance going to zero temperatures. And nowadays it's believed that physical origin lies in the interaction and the influence of the phonons, absorbing degrees of freedom, to the electron-like interaction. So it is essential for the description. Then the, I think, temperature dependence of the scattering time in all materials that changes greatly with temperature. And what else I had? Transmission of sound. Because as you maybe know, or you should know after today, the sound is a vibration of the lattice. So this is what we have to take into account, and we will start today. We'll do it also the next two lectures. We will continue with phonons. So I can write the title. So I will draw again a 2D lattice. It's the easiest, I always draw a square lattice. And at t equals 0, it does look like this. At any larger temperature, you will get atoms oscillate. And they will, they in principle can move in many directions. You always assume they oscillate around their equilibrium position at some t larger than 0. Oscillate around equilibrium positions. It sounds trivial, but then in exam, simple questions like this, people fail greatly, so I'm not sure. I just want to emphasize more. And the typical displacements are a few percent. At room temperature, they are displacing a few percent of the lattice parameter. So displacement, let's call U, U over A, it's around 2% at room temperature. However, at 1000 K, around 1000 K, sit here, Kelvin, these displacements are much larger, around, I don't know, 10, 15, I mean, at the order of magnitude, 10, 15%. And what happens when these displacements get too large? It melts. In other words, it loses its crystal structure.
Sorry, 10
Yes.
what percent?
10-15%. Well, this is all very rough. And this is at the order of magnitude. I mean, it can be 2,000 Kelvin for some, can be a few hundred Kelvin for some, so, but roughly. And you know from the equipartition of energy that the kinetic energy is equal to the potential energy, which is equal to 1/2 kBT. So equal amount of energy goes to motion and displacement. This is when you learn the harmonic oscillator. This is what you emphasize, I hope. So far it's all introduction, and I would like to spend a few more minutes on the introduction. I would like to ask you, what determines the motion of ions? It's temperature, but what gives the frequency? What determines? It has to be set up by something, no? It cannot be random. It's different for every material.
The bonding energy of neighboring
okay.
or whatever.
Good. It's determined by the bonds. How exactly? How does it enter? That's actually something you've done last time, doing Born-Oppenheimer. Oops, title I could leave. The atoms are moving in a given potential. I think Nadia plotted something of this type, no? This is the lowest level. What determines this profile?
The energy of the electrons.
Yes, electrons are determining. So this is a non-trivial concept, that ions are moving into potential determined by electrons. Do you understand? This is this is what you derived last time, I hope. So the potential you derived is the electronic potential, how to call it. And then the levels of nuclei are within that potential, much smaller spacing. And then you can have an excited state of electrons, and again levels of the nuclei motion in that potential. But we are always in the ground state, considering. So the bonds through electrons are determining the potential in which the ions will move, which will give their frequencies, determine displacements, and that's all we actually care, the energy and displacements. Before continuing with the real stuff, I would just review the types of bonds, because I noticed that not everyone is familiar with everything. So I will do the molecular bonds. They are weak bonds. I think 0.01. Yeah. That's the weakest we are going to mention today. And what determines them? Actually, next time I'll talk a bit more, but just roughly the idea. Do you know? It's the fluctuating dipole moments. So it's extremely weak. It's between noble gas atoms, like 2 neon atoms. They're just barely distorting their electronic clouds distribution when they interact. Barely distorting. It's extremely weak. But what is known, the potential, the distance, is that it has the, how did I attractive r to the 6. One can put a coefficient, whatever. And we know that it has to be repulsive when they come closer. That part is actually non-well determined. This is known experimentally, it's well known, the attractive part. The part here, the near repulsion, it's actually more or less guessed. It's a bit arbitrary. But it's often chosen to be r to the 12th because it's easy to evaluate numerically. This is the main reason. It's just twice the exponent. But this doesn't have a real physical basis, this number here. Just has to be larger, steeper. So it is something of this shape. And this is a famous potential called Lennard-Jones potential, which
What's the
describes
name?
Lennard-Jones. This is really, really short, just to be sure that everybody has heard of the types of bonds and roughly put the strengths to it, no? The second, ionic bonds. So what causes bonding in ionic crystals?
Outer electronic shell.
Yes, what kind of interaction? Here we have dipole-dipole interaction. And I'll mention it again on Monday. Here,
Electronic interaction.
electronic Coulomb interaction.
Yeah, Coulomb.
It's Coulomb interaction. You have ions, and they interact electrostatically. Actually, it is not always easy to evaluate. Again, you can come up with an attractive part, which should be of what type? The potential? 1 over r. Okay,
Yeah,
the potential, yes. Should be attractive, is 1 over r. Did they put any coefficient there? One can put this. For the repulsive, so again we have a similar thing. 1 over r is this type. Oh, and here, well, I should have drawn it a bit deeper. Okay, just approximate, always going monotonically. It's often used r to the power of m to describe the repulsive part. Whatever coefficient, did I put anything? Some coefficient.
M is
The attractive m can be varied. It depends on the cores, on the system. There are various descriptions. Yes.
Why are the processes like that?
Why?
Why we have up to power m? Why does that
It has to be something, well, more than r. It is very sharp. And then it depends from case to case. You can fit it. I'm just writing intuitively what you should get. It depends on the case, from case to case, what the best fit of m will be.
So
Yes,
for example, NaCl, what is M for NaCl?
Well, I'm not. Maybe I can find the book. I think they
Sodium
salt.
It's ionic.
Na.
Is the
And-
M integral value or it can take any real value?
Sorry.
Is the M integral value or it can take
Actually, numerically you can take whatever you want. But if you want to make a model, it's easier to make it integer. These things are actually used in some cases to model potentials. So you model and you try to make a two-body potentials to describe your system. So you don't do like full ab initio approach or something. That's a function, but you do it much simpler with this. And some properties can be reproduced. You had a question?
Yes, but this is not Coulomb potential, this to power n.
No, this one is.
Yes.
This one is.
But what
This is a core repulsion. So it's not just, it's a bit stronger than Coulomb. Yeah.
And it is just determined experimentally.
Yes. Did I put the strength? 1 to 10 eV. So we're all talking about much, much stronger bonds. And then the covalent system. This one we talked the least, actually, the least about in the course so far. It is characterized by a presence of a very delocalized electron cloud, let's say, between two atoms. This creates a bond here. It's based on the stability of each component, each atom. For this one, you cannot really make a simple description like this ad hoc. You have to calculate the bands. And a simple reasoning, how does this delocalized electron cloud between two atoms, how does it make it more stable? A simple reasoning, again, you go from the Heisenberg, you delocalize them. So you have a very spread electron cloud. But this has to lower their motion, they move less, and their E-kinetic is getting smaller, which lowers the energy. So this is like the very intuitive reasoning. But for this one, I cannot give you a simple dependence on R. The strength is similar to this. I didn't find anything but this. And finally, and I won't write anything more because we already done, metal bond, metals. This we done a lot. A presence of common metals or common electrons in the system. Which also varies, but it's on the level of EVs. These last three ones on the level of EVs, depending on the system. So each of them, you can define a potential. Even if I cannot write a simple formula like that, there is a potential. A bit more difficult to evaluate, but there is, which determines the motion of nuclei. I will expand the total energy. And for that, I will use a Taylor expansion. Right, with respect to R, with respect to, okay, around the R with a displacement A, small displacement A. So on. Let's go back one. So we will use this formula to expand the energy of our system of nuclei, which I shouldn't have deleted, okay. I can also define the coordinate system, and I define this as the vector. This is nuclei I, By the way, I'll be using interchangeably the words nuclei, atom, ion. They're not quite the same, but they always mean the motion of the nuclei plus the core electrons with it there. So don't get confused. Which has a displacement. This is the initial position, and then it has a displacement ui. So each of the nuclei has its own displacement. And that displacement can be in 3 directions. That will come in a few seconds. And then this is the final displacement I. So this is the zeroth equilibrium, this is displacement, and this is the total position of the ith atom. So I will write the energy by keeping all the atoms fixed and moving just one atom first. So I will just move the atom I in the beginning. So the energy depends on the position of each atom. It is equal to the energy of undisturbed initial system, R0, plus Ui times the derivative at R0. Plus the second derivative of this. No? You're getting the idea. Sorry, this should be directional. This is a gradient. Then I have to put the vectors. This is better way of putting it. Well, you can add also the other way, but you have to put the vector of the Ri. 0. And so on. So this is moving just one atom. But then, I can move all of them. So these were all like unchanged positions, no? Now I'm having them. That's a bit confusing. So these are all after the displacement. And again, I have the equilibrium, all of them, but now I have a sum over all the lattice vectors, I. I put delta. So this is always at the equilibrium position, evaluated. Plus the second derivative. But here I also have to take into account the XYZ components because I have multiplication of two gradients. So I and J go over all the sites in the lattice, alpha and beta over XYZ. I will have Ui alpha, Uj beta, second derivative of energy with respect to Ri alpha, and Rj beta, and evaluated at the equilibrium positions.
No 1/2.
And 1/2. It is the 1/2, yes. Of course, there are further orders we can continue, but usually this is enough to describe big majority of properties. And this is called harmonic approximation. What is this term?
0.
Just this one, yes, but what is, no. I
The
mean,
velocity?
Force.
force. It is the force. On an atom I at equilibrium. Does everyone see what it equals?
Minus.
No, this is force. Okay, we agree. This is a force. But force,
It's work.
okay, this is on an atom I. You take an atom I and all the forces acting in it, but at the equilibrium. So you forget the displacements. You just assume a perfect square lattice, no? No displacements. What is the force on an atom? 0. It has to be by definition. So this term is whole 0. Nice. And we are left with the second derivative in energy. It's the most important thing. I didn't write it so nicely. This coefficient here actually is often called d I alpha j beta. It depends on all of them. It depends on two atomic position indices, and it also depends on the directions which we are comparing.
Just the derivative.
It's the whole thing. This term, it's called d. Do you remember harmonic oscillator?
Yeah.
What was the energy dependence? You had just one particle moving. Do you remember how the energy depended on the displacement?
X. Kx squared over 2.
Yeah. There was kx squared. Now I hope that you notice these things alone, but we are getting, these are displacements. These are displacements. We even have this 1/2, which I forgot. And this thing, we expect to have the same role as the spring constant in the simple harmonic oscillator. But actually mentioning in this context harmonic oscillator, it's not far-fetched. I didn't mention in the beginning. You actually assume that each atom behaves as a harmonic oscillator, because they oscillate around their equilibrium position. Just that oscillation is influenced by many other particles. So it's not like you have just one atom oscillating. Yes, if you have, but the direction, the displacement, and the frequency depend on all the atoms around. And that's what we got here. This says here, okay, let me derive something else and then it will be easier to. So, this is the force on the atom I. Did I put any vectors? Well, let's put in the alpha direction. Can be found also as a derivative with respect to its displacement. I write I both small I and big I, sorry. This is the atom I, this is the index of sites. But they always, symbolize as the sign. Because this is equal R0 plus U, R0, you don't get anything. And now here I can find the derivative of this expression with respect to Ui. So here nothing, nothing, nothing. Here I will just remove this guy. And I will get 1/2 sum over J. J and beta, yes. And I will have derivative this I alpha R J beta. We also have the other term because it's double
We
sum.
need the UJB.
Yeah, well, you'll get it in the end.
Okay.
Plus, now I just do have the second term in this double summation. And it's all multiplied by this displacement, the other one. So this is the force acting on atom I in the alpha direction, because it's moving in the alpha direction. And yes.
Can you explain the big I is atom I and
Yes.
the small I is on a site,
This is an index of a site.
and we are finding the derivative
Of a
of
given
the-
atom, I can call it Z, whatever. So small I and J are just going over all the sites.
Yeah.
Big I is a name of an atom. I also use often small n and big N. You will see it in phonons. I get confused myself. And this, and I lost minus. I have d I alpha j beta plus d j beta I alpha times this displacement. And I will, in a few minutes, describe a bit the symmetry properties. But you can see that it doesn't depend on the derivative, on the order of derivatives I take. So these have to be the same. And I can take the 2 out. It's the sum over j beta, the I alpha, j beta, u j beta. So I got the force on atom I in the alpha direction depends on the sum over all the sites in the lattice of the product of these coefficients we obtained and the displacements of all the atoms in the lattice. So it's quite clear that this d I alpha j beta describe force constants between two atoms, between all the pairs of atoms, depending also on the directions how atoms move. They're also called spring constants, now maybe you know. So the motion of the atom I in the direction alpha depends on the motion of all the atoms in all the directions. And each of these dependencies carries its own force constant. Do you understand the concept? Good. But of course, it depends on everything. But let's be realistic and let's limit to something which makes more sense. So, maybe first neighbors? It is true, it depends on the whole. But the dependency on the 10th neighbor, it's tiny. So usually it is done in the first or second neighbors. Well, in principle you can do it for everything. But by doing this, we always have to keep in mind that we have to be within the harmonic approximation, which means that we cannot take into account the displacements, ui, uj, whatever, which are larger than some 10% of the displacement of the lattice parameter. This is the limit. So we always assume in our potential to be in extremely in completely harmonic potential, parabolic part. Okay, we can skip a bit, and I will. We already mentioned the first property, but I will write it out anyway. I'm sure you didn't use this generalized force constants and this approach to solve problems. We will derive some dynamical matrix. But actually it is, although it might be an overkill for simple systems, like we'll do 1D system today, linear chain, monatomic linear chain. You can solve it with the old way that you did probably previously, just finding the force in each atom. We'll do something a bit more complicated today, but it does pay off in more complicated cases.
So, is it the same thing like those classical problems where you have this series of masses with strings attached?
We will come to that. We'll be solving that. So, properties. Actually, at some point I should introduce a new name. Actually, this spring constant can be also called just d alpha beta, because you are in the first neighbors, let's say, and dependence on I and j is trivial because you are within the first neighbors. So unless you have so this can also, but to make sure which distances you have into account taken, it is can be written also this way, that you specify at which distance they are. I mean, it's the same thing. I think I'm using both, so. So this should be the same as which means it is the same thing what I just wrote. Oy. What does this mean? So I have here atom, displacing it. This is Ri. And then here there is a different one at Rj. And this is atom I. This is atom J. And this is Ri minus Rj. I'm trying to find the force constant, the spring constant, for the motion of the atom I in the direction alpha due to the motion of atom J in the direction beta. So this is the vector which connects them. But due to symmetry of the derivatives, it has to be the same force constant which acts on the atom I moving in the direction beta due to the atom I moving in the alpha direction. Because of the order, I can switch the order of the derivatives. That's evident?
Yeah.
Okay. So this is the first
also,
property.
Is it possible for alpha to be equal to beta?
Sure, of course. This is just the most general case, of course. That's the strongest interaction when they move in the same direction. There's the second one. I put the alpha beta. Yeah, okay, this is the one. Let's again draw. And we have Ri, Rj. And this is Ri minus Rj. This is the easiest proved, and actually this is true just in the systems which have inversion symmetry. This is not for every system. And and monatomic. This is the condition. If you have inversion symmetry, it will have to come with inversion symmetry. Then I can also take the position minus Ri and minus Rj. Now it's a bit hard to draw. There is an atom which is just at inverse position to the atom I and to the atom J. I just find those two atoms. This is R inverse and J inverse. And I find inverse. This has to be the same lattice constant. It's the same atoms, just in a different location in the crystal. But by symmetry operation, I'm coming to the same atoms. But however, the sign is opposite. So this rule is, this property is valid only in monatomic crystals, for which you can have inversion symmetry. So actually you can use translation to bring it up to the same two atoms. And you see that you can change the sign of the vector in between. And the third one, actually the number 1, number 3 you will use a lot. Oops. Okay. It's the sum of all ij, no? Yeah. Is equal to 0. So this is the sum over all r. Or you can put the sum over I and j. It's the same thing, you understand. The sum over I over all the lattice sides. Then I have to put Ri minus Rj. Or I put R and just say over all the R's. One is in the absolute rotation of the two vectors, which you have to subtract. One is in between the distances between the two atoms. It's okay? Don't get confused with such things. Let's displace all the atoms in the crystal by the same vector. D beta, all of them the same. And then I evaluate the force on atom I. Let me put it. I was deriving from the in the alpha direction, okay, and can be the sum. So the force so far was anyway sum over all the other atoms. This is not U, I called it D beta. And here it's J and beta, no? Is it correct? Yes. So if I displace them all in the same direction, I don't change anything. They are still in the equilibrium arrangement, no? You see that. And then I evaluate the force on an atom and any atom in the lattice, which I can express as the product of the spring constants and the displacement. But then this has to be 0, because they are still in the equilibrium arrangement, just shifted, nothing changed. And this being non-zero and constant, it's just a number, doesn't depend on anything, proves that this is 0. That's what we wrote right here. This is called acoustic sum rule. And this is a very important property, which we'll be using a lot. Number 1 and 3 will be using regularly. And this is also called a center of mass invariance. We are moving the center of mass in this case. The whole crystal moves. I don't change anything, so it's we don't have it here written anymore, but you've written it just a few seconds ago, the energy expansion. What we actually have to solve, it's a Newton equation for every single atom that we are considering. Normally we will stop at the number of atoms in the unit cell, which still can be very many, I mean, depends on the system. And you will have that many equations times how many atoms you have times the number of dimensions. The motion x, y, z. So if you have one atom moving in a cell, like a simple cubic, moving in 3 directions, you will have 3 equations with 3 unknowns. Okay. So what we actually want to find? Well, still not, we're not there yet. I need something more before. What is the, from the harmonic oscillator, what is the solution for the displacement of an atom I in the alpha direction? It will have an amplitude, maybe I was differently defining it. Yeah. Okay. It will have a space dependence times the time oscillating part. And this can be shown to be the only solution. We're not going to this, it's kind of, maybe you've done it actually in the exercises for harmonic oscillator. While this actually has an amplitude. So now here there is an R dependence. Here there is just an amplitude. And here enters the R dependence.
Shouldn't we include the alpha index also?
Let me see. It was there, I think? Actually, it will be here. My mistake. I is here. And here just depends on how much it can move in each direction. So the amplitude sets the maximum motion in a given direction. But it won't be moving this way, of course. It varies as a cosine. But sets the maximum motion, so it doesn't have to be, it won't be, in general, the same motion in x, y, and z. Okay. And now, we will try to come to the k dependence. Because we again want to find the frequencies in the k space. So it is something very similar to the energy dispersion in the k space. Alright, let's write the force on the atom I. I use the alpha direction, yes. And we plug in this dependence. This is omega, it's not good. So what we get? Minus second derivative in time, minus omega squared, mi u alpha times ik r I is equal u beta omega t So this goes out, and okay, minus and minus, omega square and I u alpha. Keep writing, or you can be writing alpha and beta, R minus Rj, which is the same thing. You can put these indices next to D, or you can specify their R dependence. UB. Okay. I minus Rj. Now I can write it differently. Just I can separate these two summations into summation over beta, and then summation over j I can call a summation over r. It's the same thing as we established. So d alpha beta over r, e on the minus I k r.
But r doesn't equal to 0. Or does it?
It does also, because you have also the zero component, yes. Yes. Times u beta.
Yeah.
So sum over 3 indices here, and a very nice construct that I just, which keeps in itself the k dependence, which we actually really want to get. So I can say sorry, I did not emphasize before that we are in the monatomic limit still, that the masses have to be the same. Otherwise, it's a bit different derivation, because I just realized I still have the index I, which is fine, but you have to know they're all the same masses. This is true only in the case of monatomic crystal. U alpha is equal. I will call this something else. Use the same notation. Ah yes, here I want to emphasize there is a k dependence. Okay. This, which I call now, is different. It's called dynamical matrix. And it contains in itself the k dependence of frequency. Because ultimately we are going to try to plot the frequency of the motion versus k. And we again see that it still connects the displacement in alpha direction, the amplitude to the sum of the product of the dynamical matrix and the displacement in all the beta directions, in all three directions. Which is a repetition, we just changed the space. We just switched from the real space to the K space. And this is a relatively simple starting point. When you solve problems, you can start from here or from here. Both are valid starting points if you have the data. It connects the omegas and displacements which you want to find. So you have coupled equations. Now 3n times 3n coupled equations to solve. But don't worry, you won't get a very big system to be solving. And of course, the k, as before, is given within the first Brillouin zone. So the same thing. If you shift it, you will get the same rule. We are in the same Brillouin zone, and what was true for the energy will be true for the frequency as well. And now we will just, okay, we can keep this. So actually I like this. Let me just remove this. Linear monatomic chapter. I'm quite sure that you've seen all this example before, but you've done it with forces, you know what you were mentioning. And indeed, using dynamical matrix for this system, it's a bit of an overkill. I mean, heavy artillery, but it's still, it doesn't make it any more complicated, and it allows you to solve much more complicated systems more clearly and gives the meaning, makes it easily generalized. That is spacing A, and there is an atom N that we will consider. Maybe I should use the I. That may not change. Let's use the I. And we already have the two equations. Actually, this is the general case equation. We have alpha and beta. We are in 1D. Linear means 1D. But we have only one direction. So there is no need for alpha and beta anymore. And all the masses are the same. All the, no, I want to call it N, I don't know why I'm calling for the N, over all J, and the I alpha, no, IJ times the displacement UI.
J.
Yes.
Displacement of UJ.
UJ, right. Yeah, but there is nothing else. It is that simple. This is a simplification of this expression in 1D. And what can we have here? Now we depend on the neighbors. We start from the I0. And okay, no, there is a nicer way to write it. I don't want to complicate things. I think I'm complicating it. Yeah, before I expand this, I don't want to complicate it too much. Or you can just go from here. dk, this is the same, this is the same, is equal to omega square n. So you need to find this dynamical matrix term, which was, as you can see here, defined as the sum over J. P alpha beta, there is no meaning. J of R, well, Tj is enough, times minus Ik Krj. Okay? This is the simplification to one dimension. And this is equal omega square n. So you can go this way. You can plug it in, you can do it. Or you can go from here, which kind of makes you skip a few steps. So this is probably the best starting point. Omega squared n is equal, so 0, as you asked, it does take into account the 0. T0 times nothing, there is no exponent because it is 0 here, so it's 1, plus the first neighbor, we are on the 1D, so the first neighbor at the distance of A, the first neighbor in the other direction, minus A, and let's stop at the first neighbors only. So I'm having T0 plus, and you remember the symmetry rule? T of A times 2 cosine Ka. Right? And then there is acoustic sum rule. It says that D0 plus D of A plus D of minus A is equal to 0, but D0 is equal to minus 2 D of A. That we just derived. So this is equal minus 2d of A plus 2d of A cosine Ka, or omega square n is equal to 2d of A cosine Ka minus 1. And 1 minus cosine Ka is equal sine squared. So I'm getting a minus in front. 1/2. No, it should be so minus 4 d of A. Please correct me. I can make a mistake, but then I will look for it. Ka half.
Minus?
Should be 1 minus.
Isn't it 1 minus cosine Ka, which gives sine squared? You can check, but I think it should be.
Yes, but
Yes,
this way
it is.
omega square.
You are surprised what it means. Okay. Okay.
Maybe it's because of the.
We can write it also in terms of D0.
Yeah.
And this is equal to D0 sine square Ka half. So far everybody followed. It is a simple mathematics, although it's easy to make a mistake with minus and half. And what did we get here? We have two signs of the equation, of the expressions. We got our K dependence, always as the K square, sine Ka. But in front we can have a coefficient D0 and dA. I didn't talk about the sign of these force constants. They can be both positive and negative. They can make it move, stretch more, or it can be pushing it. The only coefficient, only force constant to which I can define the sign is d0. It's the motion of the atom in its own potential, which has to be quadratic. So this one has to be positive. d0 has to be larger than 0. For nothing else, no other coefficient a priori I cannot assign. So indeed, here it's clear that d of A has to be negative because of the acoustic sum rule. Let's draw what we just got. So let me express the frequency is 2p0 over m sine square ka, or in frequency is equal the absolute value of the sine. So sine will start for small k linearly, a bit overdoing it, and then just reaches the maximum. We are going to half, which gives the pi half, which gives the maximum. Did I manage? Of course not. This is omega and k. So this is the dispersion relation of the 1D chain, linear monatomic chain. So how its frequency depends on the k vector. For k very small, sine omega is proportional to k. No, it's linear here. And the lambda is proportional to 1 over k, no? Lambda is the wavelength, which means that we are in the limit of very long wavelengths, in this case, going to 0. A few things I have to say, but I just need okay, one thing that I should emphasize here, that actually I can write for the small wavelength in the expansion, omega is equal to d0 over m k a half. Okay, let me write this a half k. This will give the velocity, it's the group velocity. It is the same principle as what we did before. The derivative of energy with respect to k. We never call it group velocity, it's the group velocity. And we see how it depends on all microscopic parameters. We have a force constant, d0. We have the mass of each atom. That's constant, which is a few angstrom. And they set the wavelength here, it is 2 pi over k, of a wave which can be kilometers in the limit. These are sound waves. How do atoms move in this limit? So displacement, there's no space anywhere. Displacement is equal to the amplitude, whatever, and then E on the IK R J omega T. When the K goes to 0, all the atoms are moving in phase, moving together. This is the center of mass motion. At 0, here, exactly at the 0. Zero frequency at the gamma point, in our case. So you're getting that all atoms are moving together, center of mass motion, a displacive mode. And this is the property of all sound waves. So here, for the limit of small k, you have sound wave. Now I really have to go. I'm very sorry. On Tuesday, I will continue talking on sound waves. Just a few more examples. Can I derive this? How does the displacement depend displacement of the atom n plus 1 and the atom n at for k equal pi over a at the edges. So displacement will depend as E on the IK n plus 1a, E on the IK n a. This gives I K A, and K is pi, the pi, right? And it should be minus 1. Yeah. So what we are getting is that the atoms at the edge of the Brillouin zone, for this K, the neighbors are moving in the opposite direction. In 1D, they're moving like this. So for K0, you have the motion of the whole crystal together, all by the same amplitude, in the same direction. At the edge, they're in the opposite. Yeah, sorry, I have to rush today. It's good to think of it. I'm not giving any homework on the phonons, but I hope you'll do some on the tie binding and the effective mass. So please keep practicing. Think of it, just analyze how it moves, what it means. It is easy math in this case, but there are some consequences that I maybe forgot to emphasize. Just make it all obvious to you, natural. So go through it with questions. How does it change, what it means, and yeah, see you.